Hello and welcome to this video on leveling up your PCB design skills. This video is going to cover a few things like routing onto layers, also things like using an entire layer as a ground plane, and also designing your own symbols and footprints for your schematics and your PCB layout. So the first example I'm going to work through, we're going to build a little shield for an Arduino Uno. So Arduino Uno being this little guy, and all that shield's going to have on it is a single 7-segment LED. So that's going to be the one that we're going to use is just this random one that I found online. So it looks like this. It drives a single digit 7-segment LED. So what we're going to do is we're going to work through the process of what would you do if you had to design an entirely new symbol and an entirely new footprint. Now, in reality, your first step would be to check if one exists or check if there's one that's very similar that you can just modify. But in this case, we're just going to pretend like there's nothing at all that would be remotely similar, and we're going to go through the whole process of doing it from scratch. So in terms of the symbol, what we're looking for is we just want to make a symbol that kind of looks nice, makes sense, and has all of the pins there that we're going to eventually include in our footprint. So you can see that this particular 7-seg has 10 pins, 1 through 10, and each of those actually correspond to different parts of that 7-seg device. So we've got the different segments like D here, it corresponds to pin 2. There's the decimal point, which corresponds to pin 5, as well as there's a common anode for power to come in. So yeah, there's a few different, that's all listed here. So this is the part that we need to worry about when we're building our schematic. And then these measurements here and this pin layout here is the part that we need to worry about when we go to actually make our footprint. So starting with the schematic, I'm just going to move this over to the side, and I'm going to go into KiCad, and within the project here, we have a couple of tools. So one of the tools is symbol editor, that's for our symbols, and the other is footprint editor. So starting with the symbol, we'll create a new one here, and we start with a blank canvas. So first thing we need to do is create a new library, and I'm going to create one that just exists within this project. Click OK, and we'll save it. So let's go 7-seg as the library. Then I'm going to create a new symbol. So File, New Symbol, or just Control New. And this is where we actually name that symbol. So let's stick with the theme. I'm going to call it My 7-seg. Here you can actually also pick if you want it to come from another device, from another existing symbol. But probably if you were going to do it that way, you would just look through the library, open it, and save an editable copy. I might show you how to do that. Oh, actually, I'll show you how to do it with the footprint editor later. It's the same thing anyway. So then we hit OK. We've created our blank 7-seg device. That's just a generic number that it'll come up with when we insert it into our schematic. So now we can start drawing. So I might just draw this as a box of some sort. And this box is going to have some pins. All right, so now we want to actually add our pins. So click our first pin. The first one we want is pin name A from our data sheet on the left here, and its corresponding number is 7. And we're going to have it point out towards the right because I'm going to put it over this way. But the next couple are going to be the same, and that was also set to default to be an output. We would change that to an input if it was something like power coming in. So then I'm going to go through and do that for the next few letters, as well as the decimal point. And you can see too, I'm going to need to expand my rectangle a little bit. It's latched itself to that rectangle. Let's try that again. And then I'm going to go through and I'm going to rename all of these. So I'll rename this one here, either by double clicking or press it and hit E on your keyboard, to B, and its pin number will be 6. And all of these are outputs, so the rest of the settings will stay the same. C is 4, D is 2, E is 1, F is 9, and G is 10. And I didn't leave myself enough for the decimal point, so I'll drag that down a little bit further and create another one for the decimal point. So decimal point is 5. So what I've done is essentially I've clustered all of my outputs on the left-hand side. Now the other thing that I want to do is the other 2 pins that were listed, which is the 2 common anodes, pin 3 and pin 8. And I'm just going to pop them both over the other side, and they're going to be where our 3 volts comes in, our 3.3 volts comes in. So I'll call that common anode. And that can be pin number 3. And that's going to be input. And I'm going to have that one point to the left. So I'm going to whack that one down here. Let's put it in line with G. Actually, I could probably just call them both CA on its own. So this bottom one is going to be pin number 8 from our data sheet. And that's my symbol pretty well done. I can do a few like beautification things, like if I want to, I can actually assign it a background color, which is what the default ones have. And the default ones are usually a nice yellow color. Let's say it's a green LED and I might want to make it a very pale green to represent that. I actually don't remember what color it is, but let's pretend. Cool. So that's our schematic symbol done. Save that, and we would now be ready to go and put that into our schematic editor. So close this off. I'll head into my schematic editor. You can see I've already inserted my Arduino Uno, and I've already sort of decided which pins are going to drive which part of my 7-seg that I'm about to insert. So pin 17 on the Arduino is going to be connected to the G pin on our 7-seg. So I go into my parts list, and I can look for that symbols library that I just created. So what was it called? My 7-seg. There it is there. And I'm going to pop that one on the board somewhere. And then I just need to wire it up to my Arduino. So currently these labels GFE, they're not directly connected to this yet. That's what we call I think they call them a net label. So that G needs to still be added over here, again, as a net label, not just as a schematic label. So to do that, you can press L on your keyboard, type in what you want to call it, and drop it there and wire it in. And then you just repeat the process for all of that. So I'll quickly do that. All right, so that's everything connected now. So instead of having kind of big wires going all the way around and crossing over each other and looking really convoluted, I've used that function that I just showed you of placing the net labels to actually say, okay, A here is connected to A here. B here is connected to B here. You could just draw a wire going all the way around to A, and you could do that for all of them, but obviously that gets pretty messy pretty fast. So this is just a nice way of keeping that neater. So that's all wired correctly to our Arduino now. You don't need to worry too much about what the Arduino is actually doing. Essentially, it would have some code that pushes information to each of these pins to control this 7-seg, but we just care about the actual hardware for now. So what this little piece of 7-seg is currently missing is a footprint. And again, assuming that there wasn't already one that existed that did the job, we might need to go and design that footprint ourselves as well. So again, in a data sheet for a standard component, you'll see that most of them will provide pretty detailed specifications about the size of the component. So here you can see it's given you sort of the distance between components, the overall size of the sort of rectangle that goes around it, and all the hole spacings and that sort of thing. So how can we use that? Well, we can go back to our KiCad project. We can open up now the footprint editor. Giving me some errors because I deleted some, but that's okay. Then we go through a pretty similar process to what we just saw for the schematic. So first things first, we're going to need to create a new library. Again, I'll put it just in my project, and I'm going to call it 7-seg again. So that's now being created and added here, and now I can start actually drawing. Sorry if your screen just glitched. I managed to kill KiCad in the process of creating a new footprint, but here's our new footprint now. So once you've done that with Control N or just by going through the file menu, it'll have sort of some blank reference stuff that we can deal with later. For now, what I'm going to do is I'm just going to move it off that origin point because I want to put my very first pad, selecting the Add Pad button right there. And by default, it wants to make it a surface mount pad. What we actually want is through hole looking at the data sheet. And we probably want it to be round because it's suggesting a circle on the data sheet as well. We want the first pad in the top left corner to be pad 10. So I'm going to call it pad 10. The size of that, I'm going to make a little bit bigger because the hole size needs to be 1 mil. So to leave myself a little bit more clearance, I'm just going to bump it up a touch to 2 mil. And that's all we really need to set up there. Then we have everything else I think we can leave. Yep, cool. All right, so then from there, we can just copy and paste that a few times, and we can just adjust the position accordingly. So from our data sheet, each one needs to be 2.46 away from the previous one. So that's all in mils. So we just need to keep popping them along another 2.46 further away each time. And yes, I am doing this with my calculator because it is too late in the day. And assuming I've done the math right to that point, the last one should be 9.84 over because that is what the data sheet said that the overall distance between them would be from left to right. So now I just want to go through and name these. So again, looking at the data sheet, it descends from 10 to 6. So 9, 8, 7, and 6. And what this is doing is it's actually linking that to the same numbers that were in the pinout for our symbol. So pin 10 is connected to pad 10, pin 9 is connected to pad 9, and so on and so forth. So that's one row done. Looking at our data sheet, we then have another row that are 15.24 below that. So we can actually just select the lot of them, pop them on that origin as best we can. It likes to be a bit tedious when doing this though, so I'm probably just going to have to quickly manually pop them over to where they needed to be. And then we can change their Y position all at once. So for that, we want to put it 15.24 down. And I set everything on the origin, so it's just going to be 15.24. Now I'm going to select this stuff, all of the kind of stuff that'll be added as text. And I'm just going to pop it somewhere roughly in the middle. Not going to be too fussy with it, even though it'll probably annoy me later when it's not perfect. And I'm just going to change this untitled to be a value of 7 seg. You'd probably more realistically give it the actual part number. Alrighty, so that's oh, hang on. The other thing I need to do is go through and change these numbers. So down the bottom, it was 1 to 5. So 1 for that one, 2, 3, 4, 5. And then we can do just beautification stuff if we want. So functionality wise, this is done, you could leave it alone. But if you want to make it look kind of pretty, what you could do is you could put a rectangle around the boundaries to make it look nice and contained. So that should be pretty close to centered as well. You could even draw a picture on the middle if you wanted. So for example, if you wanted to actually draw a symbol of an 8 seg, I could move all this stuff out of the way. Move it up higher. And I could actually put like a little 8 seg symbol on here if I wanted to. I might even put this one. No, it doesn't want to go outside. So I could actually go through and I could draw like 8 segments up using rectangles or something like that. Probably won't go through the full process because it gets a bit tedious, but you could actually make it look like this by using the polygons and the rectangles to draw it. Cool. So given I didn't do that, I might just recenter those. And I'm going to just save this as it is. And I'll give it a name. So I think I called the last one my 7 seg. So I'll stick with that because it's now going to be saved as a footprint file anyway. The library has to be picked. So we want to pick that library we created before. Normally it'll do that automatically. It's probably just because I accidentally killed KiCad somehow by hitting Control N. So we'll do that, and it'll pop it into that library there. So that's our footprint done. Now we can go back to our schematic editor, which I'll need to open up again. Yep, it failed because, again, it crashed. So now we can save that. That looks like it did actually autosave everything correctly though, so that's all good to go. And I'm going to assign that footprint. So edit it like normal, go to the footprint library like normal, and now you're just looking for my 7seg in that 7seg library. And you can even have a look at it in 3D view, but it's not really going to show you much because it's just blank currently. Cool. All right, now we can go over to our PCB editor. We can then update our PCB from the schematic. No warnings, no errors. We can drop everything in. Now, because this is a shield and not an actual Uno, we pretty much want to flip this so that it would plug into an Uno. So it ends up having the pin out more like this shield I've got here. So, I mean, it's going to be impossible to visualize through my camera currently, but I'm just going to right-click and flip is what I'm getting at here. Then I can move my newly developed 7seg, and you can see that's the footprint that I designed, into here, and I can position it where I want it. So let's say I want it to be facing up like that. So that would be where I would put it for that to occur, more or less. So that's the journey you would take from sort of creating a component symbol through to creating a footprint through to actually placing it on a board. Now, in your actual assignment, you're not going to have to create anything as complex as a 7seg LED. Probably the most complex one you'll have is your microphone. So for your microphone, if you can't find a component, a footprint that makes sense for you, there are a few available that probably will work for you, but that might be one that you want to design yourself to get it more perfect to the exact shape of your mic. For anything else, really, you would expect to find a pinout that works and a footprint that works. So have a look at the existing libraries first, but if you do want to try and make one that's a little bit prettier for your microphone, then please feel free, follow this process, and you can go from there. You can also create new footprints for an existing schematic. So for the microphone, there's definitely an existing pinout that is just like the plus minus done. So just like any other header. Then you could go and assign a microphone footprint to it that you have designed to correspond with those pins. So that's a nice streamlined way when the symbol exists, but the exact pinout that you want doesn't exist. Anyway, that's a bit of a side note. The next thing I want to show you is what happens when we have messy routing. So in this board, you can kind of get the gist by looking at the way that this is laid out, that there's not really going to be a nice, clean way to actually route this all together. So if I was to start, let's just pop some wires down. So also, I should also mention setting up your design constraints. So I actually did this earlier. I've set it to the constraints from, oh no, it's cleared it probably because it died. All right, what I'll do is I'll import it from an existing board that I've got. So if you've already got another board that you've already designed for JLC or for the milling machine or whatever, this is one from the next video that you'll watch, then you can actually import that and import the existing constraints from there. In that other video, I go through the full process of how we set up these constraints though, so make sure you do watch that. I can also predefine my track widths, so I'm going to make some, maybe, let's go with 0.3 mil width. That way there's sort of a decent thickness there. And I'm going to have some vias here too, so I might also add a predefined via size of, let's go 0.4 with a 0.25 hole. Oh, it probably doesn't actually need to be quite that big. Let's go 0.35. Cool. So once those constraints are set, you then just want to pick from the track list the track size that you want to use and the via list the via size that you want to use. So now we can get to work. So on the top layer, what I'm going to do is I'm going to start off with connecting these two pins that are connected together and then up to the top here. And you can see now we immediately run into a problem where if I want to take this one around here, there's not really a nice clean path I can take. So this is where two-layer routing comes in handy. So if I go to my back copper layer, I can do that track without creating any electrical problems, fairly nice and simply. So I can go around this way. That's probably going to create problems later on though. Let's start with some more of the top ones. And now again, we kind of run into a problem here where it wants to go like around the outside and it's a little bit messy. What I could instead do is come down to here. I could punch a via by pressing V on my keyboard, clicking, and then carrying it across to here. So we've been able to continue that trace on the other side of the board. And it would cycle through multiple layers if you had more than 2 layers. Then we can continue on. This one's pretty good there. This one's pretty good there. That's all happy days. And then these ones are going to be a little bit more complicated. So again, this one we run into the problem now of we would be crossing our own blue tracks. So we want to get into there. We could probably do it a few ways. Actually, I might delete this other trace from before and redo that one once I've got this one in. So let's do this one first. So I'm going to come to, let's say here, punch a via. So V on your keyboard, click, and then continue. And then I'll do the next one. Again, extra route. Again, come around. We're going to run into a problem where we have to cross tracks. So get to here, punch a via, come across. Then we've got one more. So this one might even be worth just routing on the top layer, but let's have a look. So X on your keyboard to start the route. Yeah, let's just put it on the top layer. So go back to our top layer, route that down, and then we only have one left. I'm going to start this one on the back. And I'll come down to, not really a nice clean way to do it with how I've gotten so far. All right, let's punch it through here and then around the outside like that. Cool. What does it not like there? Oh, there's still a residual via, so I'm just going to delete that via from earlier. All right, so that doesn't look too bad. Almost certainly you could do a better job if you spent some more time on it trying to figure out the best way to lay these out. But the key point here that I want you to take away from this is sometimes it is pretty much impossible to route a board without having wires that would eventually cross if you went on all single layer. So in these cases, it's essential to do 2 or more layers. But even in some cases where it's not essential, it can make it nicer. So it can make it a lot neater to go kind of under a trace and keep a fairly direct line and keep going. So everything here now is electrically connected with a combination of top and bottom routes. The only thing that's missing from our overall design, hopefully, is the edge cut layer. So let's draw that in. Oh, I always do that with the rectangle tool. There we go. That's our edge cut. And we can run our design rules checker to make sure I haven't overlooked anything. Errors and warnings. What are the errors about? Hole size out of range, minimum hole 0.3, actual 0.2. I made my bias too small. Right, all right, well, I can select all of those by highlighting them. Right click, go to select, filter selected items, and I want to only include bias. And rather than changing my constraint, I'm just going to make those a little bit bigger than they needed to be. And we'll see if that satisfies the design rules from JLC now. All right, annular width of the via is too small, so I need to make the actual pad size a bit bigger for those as well. So same process to edit that. So roll on. Cool. No errors left. The only thing left is a warning for the thickness of the text because the silkscreen text thickness has to be at least 0.16 by the JLC design rules. Again, more on that in the next video, so I'm kind of sneaking you a peek there. But if we want to go to just that silkscreen text, we can bump that up to 0.16. just makes it a bit chunkier so that it's easier for them to print. So let's take a look at what this looks like. This should now pass all our checks, and we can have a look at what it looks like in 3D. So it's a pretty simple board. The only thing we've got is one component. We're only driving one 7-seg, and you can see the top looks reasonably neat. It's got just a couple of traces, and then the bottom also looks reasonably neat. There's some more traces, but they all kind of are fairly straight and following a pretty neat pattern. Obviously, this is a very simple design. A typical shield would have a lot more than this one 7-seg, but that's that all sorted there. So other things you could add to this, another thing that we haven't really done much of yet is silk screening. So when we actually send it to the manufacturer, you get your green solder mask, and then on top of that you have your silk screened text and anything else you want to put on there. There's ways to add images and stuff. They're a bit roundabout, but if you're interested, let me know and I can point you towards some resources. But the one thing you should definitely do is you should put your name on your board. So for now, I'll put mine on the silk screen on the edge cut layer. I can change the thickness to be what was required. I can change the height and width of the text as well if I wish. I can make it bold, I can make it italic, I can do whatever I like. And then I can just pop that somewhere on there. And here you will then see when we go into our 3D view that we've now got my name on the corner there. So it's definitely something you should do to make it easier to find yours when you actually design and we send it away. The other things you might like to silk screen here are things like 3V 3. That would be an option. You could also silk screen particular pin values if you wanted. If this was a specific part number, you might silk screen that. But overall, that's kind of what you'd be looking at. So once you've finished your board and you're ready to export it, you'd go through the process of exporting all the files, including the drill files, the silk screen, and everything else. And that would be this board done. Now, the other demonstration I wanted to show you is what happens if you can route everything on a single layer. With JLC, it costs the same to do 1, 2, 4 layers. So you might as well make a ground plane one of your layers. So what might that look like? Well, let's open up another example. So I'm going to go open up another project. So we'll open that up, save all of our changes to that. All right, so for our second demo, we're actually going to go back to the basic rectifier circuit that we did previously. And I'm going to show you with this one, like when you don't have a very complex board, how can you make use of that second layer given it doesn't cost anything? So if we go over into our PCB design for this, you can see I've left it blank for now. Again, we want to go in, set up all of our design constraints before we get started. Set up our track width that we want to use. I've picked 0.2 mil as my preference here. I'm not going to have any bias because I'm going to intentionally route this all on one side, so I don't need to pick that one. If you do, make sure you pick it to meet the design constraints, unlike I did before. And we want to then update our PCB from the schematic. No warnings, that's nice. There's all our components that we know and love from previously. And we want to just go through and quickly lay these out. That's everything laid out. And what I want to do is I want to firstly route together the stuff that is not ground. So on the back layer, I'm going to start routing. And that one. And that one. Actually, I'll route from there to there and then around the outside. So that's all my non-grounds routed real quickly. And that's all at 0.2 mil track width, which is much smaller than we needed for the milling machine because this one would be being prepared for JLC. Then we can go to our copper layer, and here we can draw a filled region. So draw our filled zone around the entire area that we're interested in. So we want to go click, select that we want it to be ground, and we just want to make a fairly neat rectangle around the outside. And we're done. All right, then we click B to fill. Away it goes, and you can see all of our blue guidelines have gone away because we've filled the entirety of our top layer with copper. Why would we want to do this? Well, if you've got an entire plane free, you might as well, because it's really good for signal integrity to have just a big empty piece of copper connecting all of your grounds together. So this is a really nice way to make use of a currently unused second layer. Like I said, it doesn't cost anything extra to do this. So I also probably made it a little bit too close to the top there by JLC's design rules. So I'm just going to move that out and fill it again. If you do change it, you do have to fill it again. Now that looks really good. So actually I think I'm missing a trace there by the looks of it. So where's that one supposed to be connected to? There, cool. So yes, this is really good for signal integrity, like I said. And in fact, if you went to production level boards or more complex projects, even more common is to do 4 layers, where you'd have one big flat plane be your ground, one big flat plane be your power, and then 2 layers of actual tracks. Again, that doesn't cost anything extra with JLC. Anything up to 4 is the same price. So yeah, that's kind of what we're looking at with our ground plane being a whole plane. Again, you would only do this if you didn't need to route on both sides. If you did need to route on both sides, the best option then is to turn both layers into a ground plane. That way you've got plenty of copper on the top, plenty of copper on the bottom as well to be the ground plane. And it's not as difficult to solder when we're getting it from JLC because you get the solder mask that stops you from shorting to your ground plane like you might have had happen during your milled board experiments. All right, so that's the actual functionality done, but if we had a look at the 3D viewer now, we would see that it's a bit of a mess in terms of the silk screen. Like stuff's just kind of thrown around everywhere. So what we're going to want to do is we're going to want to clean that up. So I'm just going to hide the layers here, and I'm going to start moving stuff around. So none of this gray stuff actually matters. This is all just references. So we can delete anything that's gray just to get it out of our way. Preferably not the whole component though. And what we want to keep is the yellow labels. So D1 belongs there, D2 belongs there, D3 belongs there, and D4 belongs there. And then RL1 belongs there. Given there's only one of them, we might even want to change that name to just RL. And same with this J1, that's not very descriptive, so we might want to change that to something like AC in, and we might want to rotate it around and pop it somewhere, say there. Probably could have brought those a little bit closer together too, but that's fine. Then let's have a look at the sides of our board. I'm also going to add in my name because it's always good practice to add in your name. Enter that. Thickness is fine. I want to put it on the silk screen though. Must have not selected that here. So I want to make that. So I want to make that thickness a little bit bigger. Pop it down on my silk screen this time. And that should be everything I need done. Add an edge cut as well so that it actually knows where the edges of the board are. And go to our 3D view. And you can see there, I've turned off the through-hole components so that we can see our pretty little silk screen. You can see it looks absolutely lovely. We've got copper everywhere except the pads here. So the pads are isolated where they need to be, and they're connected to the ground plane where they need to be grounded. And then on the other side, we've got just our nice couple of little quick traces. I probably could have done a neater job of that, but hey, it wasn't really the point of this video. So that is our board then ready to go for production. Again, I'll go through the process for exporting and checking how that all looks in JLC in the next video. But that is pretty much the skills I wanted to cover here. So now you've seen a bunch of things from designing your own symbols to designing your own footprints. You can do one or both of those if you need to. Then you also will be able to route it in a few different ways, either 2-layer where you set your entire front and bottom as a ground plane, and then you have your routes carved out. Or if you only need to route on one side, using your other layer as a ground plane to create that really good signal integrity. So that's a really nice option that we've got. You've also seen how to silk screen so that you can label everything up. You can even label specific values if you want, though I don't really recommend it at this point because you might find that even though you calculated theoretically that you wanted a 1K resistor there, experimentally you find it works a little better with a 800 ohm or something like that. So you probably don't want to commit to values when you're silk screening at your early stage. Hopefully you found this skills video helpful. If you have any outstanding questions, please let me know, and I'll see you in the next video.